Good afternoon, everyone. It's my pleasure to welcome you all to this NAI ScholarShare from UNC Charlotte. Today's conversation is entitled 2 + 2 = 5, The Joy of Invention, a reminder that true breakthroughs rarely follow a linear path. They happen when rigor meets curiosity and when someone is willing to pursue an idea long enough for the unexpected to emerge. Dr. Ishwar Aggarwal, his career exemplifies that mindset. One of UNC Charlotte's most inventive researchers, he holds more than 100 patents, and over the course of more than 5 decades has fundamentally changed how infrared technology is used. He has moved it from laboratory limitation to deployable systems that protect pilots, enable advanced microdiagnostics, and strengthen national security. His inventions didn't simply improve existing tools, they created entirely new capabilities. What's especially notable is the breadth of his impact across industry, national defense, academia, and entrepreneurship. In every setting, he has translated deep science into real-world outcomes. Today, first we'll learn about Dr. Aggarwal's cutting-edge scientific research, and then shift to a broader discussion about his journey behind those breakthroughs, how invention actually happens, what sustains it over a lifetime, and the life wisdom gained along the way. The chat is open now and throughout the conversation, and we invite you to jump in with your questions as they arise. Dr. Aggarwal, thank you for joining us.
Oh, thank you, Laura, and thank you, NAI. I really appreciate this moment to share my thoughts with many people. As Laura said, I'm a professor at UNCC these days. I have a what happened to my yeah, that one. Uh, Yeah, like Laura said, I'm lucky enough that I have my career has been in all three phases. I spent 12 years in the industry. I spent almost 25 years in the government, not planned. And now I'm at University of Charlotte for last 14 years. In the industry, it was very different. I started my work at Corning, which was very interesting. That were the beginning days of fiber optics. So I can call myself as one of the inventors of the so-called telecom fiber optics. Then I switched to two smaller companies where I set up a couple of fiber optic factories where they made the fibers. And finally, in industry, I also went to Lasertron, where I learned more about the lasers and semiconductor technology, which was not my theme in the beginning. After 12 years in industry, I went to Naval Research Laboratory, where a lot of the patents which I'm going to talk about have happened because that was a research kind of position. And after that, I come to UNCC for 14 years ago. So talk about my work all has been in optical materials, and optical materials can be of several kinds. One of the optical material, one category where I work, and I do have a lot of patents and a lot of literature in that area, is IR fibers, IR sources, that means LEDs and lasers, and amplifiers. Then second thing is making windows. For example, in this case, I'll come back to the fibers area a little bit later. In this window case, if you have an aircraft, in the aircraft, you need some windows because they put in reconnaissance aircraft, especially they put cameras, and cameras that look through the window. And these windows have to be two things have to happen. Windows have to be very, very strong, and they have to be able to transmit the light. And a lot of the times, light is both the infrared as well as the visible. So the windows has to be clear for the visible as well as infrared, which is not found in many of the glasses. So we had to make special glass materials to do that. The third kind of materials are crystalline materials like sapphire, diamond. They are crystals, but they are single crystals actually, and then there are polycrystals like spinel, which I'll tell you more about that. That we played a lot of game in the spinel. Now talking about the fiber area, for those I'll try to make it as simple as I can. who are not in the industry. When you look at there are four categories I showed to you here. One is a silica fiber. Silica is basically sand. So that telecom fiber which you use today in everyday life was invented 50 years ago, low loss fiber. That was silica fiber, and it goes only in the near infrared light, around 1.5 micron, if you know the wavelengths. Then you get into the infrared region, which was not available before we came to the scene, and we try to make these fiber to be low loss. And I'll tell you more about it. Sulfide, selenite, telluride. These are so-called chalcogenide materials. And we have to make stable glass with that so we can draw the fibers. And those are the things we talk chalcogenides. And they transmit in near infrared, mid infrared, and long infrared. So now, where do we use these fibers? The telecom fiber, I already talked to you, that's used in telecom, and I'll not talk about that more because it's used in everyday life. And my first 12 years were in the silica fiber. The next type of fiber is called the infrared fiber, as I mentioned to you. Where that is used on if you first let me before I go to that, let me tell you what fiber is all about. Many people don't know what fiber is. A hair thin glass fiber. Now in this fiber, it's not simple one glass. It has two or three glasses. You make a central glass, which you see in the right hand side over here, and then it's covered by another glass. Though there are two cylinders which go in, and so you put the light into the central one. The other glass helps reflecting the light back into that core, what we call as a core, and we call it as cladding. So what happens is this light over miles and miles, this light doesn't come out of the fiber. Even if you bend the fiber, do whatever with it, light still remains in the fiber. That is called fiber optics. And we make it, it's like a rod and tube. I'm showing in a very simple way. It's not the way it is made these days, but you combine a rod and a tube, and then on the like in the middle, you see a fiber drawing tower. You hang the fiber in a furnace at the top on the second floor, then you draw it. Fiber is drawn by these wheels which are shown in the bottom. And on the right hand side, you see the spool of fiber is a red fiber because it's infrared transmitting fiber. Then you have to, on the fiber, you have to put some clothes on. That means you have to make a cable out of it. And once you make a cable out of it, then you can use it. In my next view, guys, I want to show you how it is used. Normally, the biggest problem when I joined the military was that the helicopters were being shot by the oncoming heat-seeking missiles. Heat-seeking missiles have a sensor in them, so it follows the engine of the aircraft, whether it's helicopter or a small aircraft or large aircraft. And the way to defeat that is you throw a laser light on it, confuse the heat-seeking missile or the seeker in the missile, which is seeking the heat, confuse it, and you confuse it by putting the laser light on it. So how do you put the laser light? Basically, you can put a laser in the belly of the aircraft, but then your jam head or the device which is going through or which will find the missile and throw the light on it, it is at the wing. So you need to transmit that laser light to the jam head. That's where our fiber was used. It was very critical at that time, and the fiber done fantastic thing because you can, using the fiber, you can have 6 jam head, top, bottom, sideways, and you can only use one laser. That was beauty of it. So other place where infrared gets used in sensing system, for example, your blood. Your blood is tested by the infrared light. When you look at the, sometimes you put your hand on the light, the infrared light goes on, reacts with your blood and gives infrared signatures. Normally, these infrared signatures are all in infrared. The second the slide on the top, where you see these are the CH and bonds which are in the infrared, and you get the signal from these bonds. One of the things we did with these infrared fibers, we designed sensors which could detect spills inside the ground, etc. And we made a sensor so we can just dig in the ground and it can find out how much of a gasoline or diesel fuel or something is spilled in the ground. That was important at that time. That was base cleanup system. But you can use these fibers or these systems for measuring or detecting chemicals, any kind of chemicals. You can design the system. So infrared fibers were very useful for those both the things, sending the infrared light for defense purpose as well as for commercial and sensing. For those who are deep into physics, you can play a lot of other games. When I said 2 plus equal to 5, that's nonlinear thinking. So nonlinear thinking goes into physics also. In physics, you have so-called nonlinear phenomenon. For example, in this supercontinuum where I say in this view graph, you can pump one wavelength of light, and if you can play the fiber properly, you can have 6 or 7 colors coming out of it. That's called supercontinuum generation in a fiber. And that's a really fantastic thing. It was found like in about 20 years ago. But you can do other things. Other things is you can use these fiber amplification, where you put a pump light and you put a signal. The signal gets amplified. Or you can also you can put a pump in and you can get two different wavelengths of light. This is all nonlinear effects and nonlinear thinking. Then third one, Raman laser, you can shift the wavelength of light. Suppose I don't like the color. The color, I can generate a laser color, for example, a 2 micron wavelength, but I need something at 4 microns. I can use this fiber, do the parametric oscillations, and then you can convert that wavelength into different ones. So there, for physics type of people in this one, this is a complicated view graph. You can do a lot of these things, and people do it. And we have done that. We have demonstrated in our labs. The other invention, totally away from the fiber area, I'm talking about making ceramics. For example, you have toilet bowl that's made of ceramics. But how do you make it transparent? That was the key at that time. Sapphire and diamond are single crystal material, but very expensive. But can I make a sapphire-like material using other chemicals? That was what we did. Spinel is a aluminum magnesium oxide chemical. The property of spinel is very similar to sapphire. But how do you make it transparent? We start with a powder, which is shown on the left-hand side. What we do, we make a puck out of that and press it at very high temperature, at very high pressure. And what will come out is a transparent material. But historically, before we got in the scene, the material used to come out is looking like turbid on the right-hand side, where it is written historically spinel was difficult to make. But then we came on the scene and we used some of our techniques. We made it extremely transparent. For example, you see in this slide, this spinel, sapphire-like material, first of all, you can make in big sizes. It can be used as a bulletproof glass. Example you see is like president's car. When you see the door is about 4 or 5 inches thick, or maybe even more than that, because they use a bulletproof glass in the windows. But if you use the spinel to make that bulletproof glass or bulletproof material, that will be 1/3 of the thickness. So the weight will decrease. And they are actually doing it right now. After we have made these materials to be very, very transparent, now they can use it. On the left-hand side, you see in the soldier goggles, because they used to get shot in the eyes and things like that. You see the bulletproof glass where bullets are shot, but bullets don't penetrate through. On Humvees, on the helicopter doors, because they were being defeated. So there are many applications. Then in commercial application, that material was fantastic. You can use on your tablets, TV screen, in case you want to do that. Right now, they use a Gorilla Glass or they use sapphire for the watches, etc. But you can use a spinel if you want to, and if you want to develop that material for that. So another one last inventions I will tell you is about reflection. For example, when you look at the car doors, you can see your face. When you are seeing your face, that means the light is being reflected from the from the car, or any glass surface, any transparent surface will reflect light. It depends on the refractive index of the material, how much it reflects. But normally it's reflected about 10%, 20%, something like that. In simple glasses, household glasses, which you use, you reflect about 10%, 5% from each surface. So what do the doctors do? They put anti-reflection coating on it. That anti-reflection coating basically eliminates the reflection coming from the surface. You see these eyeglasses, one has the reflection coating, one does not. So you do that. But these coatings, in our case, we are developing very high energy lasers. When you have a very high energy laser and you want to pass through the optics, that coating burns off and peels away and damages the laser. So what do you do? Because coatings don't work in the laser area. So in laser area, somebody, I mean, this will be very interesting to most of you, is that they found out the moth's eyes. Moth's eyes don't reflect. So they wanted to find why the heck their moth eyes don't reflect. Because they have microstructures on it. Because they have these prongs, like you see in the picture. These are moth eyes have submicron cones in the cornea, like 220 nanometers, submicron or nanometer kind of. So if you put that on, then they don't reflect. So we did the same thing. We made surfaces with the, as you see here, which I can't go in that technique because of the time. We etch the surface in a proper way. And if we etch the surface in the proper way, we can create a structure like you see in the picture above, a rough structure on the surface. You can see it. These are nanoscale thing. On the surface, it will look like it's plain, but it does have a structure on it. And when you put the structure, the reflection loss goes away. Like transmission becomes almost like 100%. It is shown in the graph. We can do that on the quartz glass. We can do other things. When we did this thing, it really makes it fantastic. You can transmit very high energies. It is shown here at in our labs at UNCC. We made small samples. We made big samples. And then we tested these samples in front of a 100 kilowatt laser. I'll go slow on that one. If you see on the left-hand side, we had a laser 100 kilowatt. I can show you the actual picture. That laser, if you put for 20 seconds, on the right-hand side, you see a brick. It it creates a hole in the brick in 20 seconds. You see this round hole, perfectly round. That's done by the laser. But now it can burn that hole, and that is the purpose of doing that laser, because we want to shine the laser light on any enemy's missile or enemy's aircraft and things like that. That's being used for damaging the aircraft in case we have to do that as a defense. So that's the laser is going to be used for, as well as will be used for industry, working with metals, cutting the metal and things like that. So you can do that. But you need a window for the laser. If you need a window, you have to have a window which can survive that 100 kilowatt right now, but in future it will be 1 megawatt, 2 megawatt, 3 megawatt. So that light has to pass through. We made a window with the moth eye structure, which I just talked to you a couple of minutes ago. That laser window was kind of 8-inch in diameter, but we shine 6,400 times more intensity on that window, and it survived. It did not damage. So that was the claim to fame, because we were able to make the windows for very high energy lasers because of the moth eye structure, because we saw some effect someplace and we were able to reproduce that. So this is the beauty of when I say 2 plus 2 equal to 5, that you can do things. You can have one invention, then you can couple with the other invention, and you can get a third thing, which comes out to be very, very good. Just one case in point, just giving you an example of 2 plus 2 equal to 5. You'll ask me, why do I say that? You have a somebody has a pot and another person has a handle. So you put the pot and the handle together, it becomes a bucket. Now, bucket is a lot more important, a lot more interesting, it can do a lot more things than the pot and the handle itself could do it. So that is my point, that you can make 2 plus 2 equal to more than what the individual things were. And that's what we did in all our technologies. We combined the ideas from several technologies and made the technology happen.
Well, I'm going to come back in here. Dr. Aggarwal, thank you so much for that tutorial. I mean, your inventions are amazing. Your expertise over almost 50 years in industry, in academia, and in the government show extraordinary depth and creativity. And Can you take, for people that are interested in how they can develop 2+2 and nonlinear thinking in their own minds, can you take us to a time in your career when you actually created something nonlinear and how that came about in your thought process?
Yeah, it comes many times actually. We were working on the telecom kind of fiber in the industry for 12 years. Then I joined the government. I joined the government because they had another kind of fiber which was supposed to be ultra low loss fiber. And that ultra low loss fiber was made of Z-band glass. And another glass, I won't describe that in detail because of the timing. But that's supposed to theoretically it did give the loss, which is supposed to be 100 times lower than the telecom fiber. Now, but we could not make it because we couldn't get to the purity level needed in order to reduce the glass. We developed the purification processes. Now then, I was at a standstill. That what the heck we do? So we did the best in that. Then I changed the program to another kind of glass, the infrared glass, infrared fibers. But infrared fibers was never were used because they were high loss. Their loss was very significantly high. So we use the technology, purification technology, what we developed for the fluoride glass. We use the similar process to do the purification of the materials for the chalcogenide glass. And what we know, me and my team at NRL, we were able to get relatively very low loss. Relatively speaking, it was like hundreds of dB per meter, and we reduced to a fraction of dB per meter. And that opened the gates of many applications, as I mentioned to you, in helicopter protection, for sensing devices, for many other things. So you take one technology, if it doesn't work, you put in the another one, it may work. But the idea from one you combine in the other one, and it starts working.
Well, and we've had this conversation about how you try many different things over and over again.
Oh, yes.
And Thomas Edison famously said, I mean, I'm paraphrasing here, that he had, 1,000 failures before, 1,000 tests that failed before he came up with the one invention. So can you reflect on that?
Yeah, yeah, of course, it always happens. You try so many things in the lab, you have to be persistent. That's why in science and technology, I used to tell myself and my scientist that you can't have bright results every day. It's 99 results are bad results, and then one day your technology succeeds, and then you carry on that. That always happens, and in research or any other idea. Even many people say in businesses too. Sometimes you go bankrupt, like well, I in several companies, and then all of a sudden you find one where you are really successful and you make up for the losses you had before.
But what
So,
gives you the persistence to keep on trying different things?
well, two things. One is survival. Of course, you have to work, you have to earn money. Secondly, uh, there are always, even in the technology which we do, there are always bright days where you are using one. At NRL, what we did is that we always had to have three, four programs going on in parallel because uh, uh, the old days you could take just one program, money will come in, and you keep on working on it, working on it, working on it, and you become the totally expert in that technology, and that then you can get Nobel laureate kind of work because you are working in technology for 50 years. But at NRL, every 3 years, we start one idea, one technology. If it doesn't pan out, if it doesn't go to the next level, then we have to get another idea. So we were always seeking ideas. When you go to conference, basically our meeting was that what are the new things we saw? What are the new programs we can do? So every 3, 4 years, I had to start new programs. When you start new programs, so tenacity comes. Some programs are giving you the pleasure because they are successful. They are going to the next level. Some programs you find roadblocks, and how the heck we solve the roadblock? And many times you have to solve the roadblock by analyzing the problem. That's one thing I want to stress on people. Some people have tough time saying, I don't know. In research, you have to find out, really analyze the problem, find out what you don't know. And if you find out what you don't know, then you can ask a lot of stupid questions to the people who know something, so you can find answers. So one of my biggest deal I used to do even with the people, that how long does it take for it? I'll keep on talking. How long does it take for a candidate, if I'm hiring one, how when he will say that I don't know? The time he says he doesn't know, I appreciate that. Because a lot of people give long answers, winded answer, and they don't know the answer. You know that he doesn't know the answer. If you tell right in the beginning, you don't know, time is over, then you can find out the truth. So
Yes.
that's one of the things I would say. You do PhD just to find out what you don't know. Not that what you know, what you don't know. And that's very, very important. It's very important that you find out what are the where the roadblocks are so that you can fix it. Where the problems are so you can fix it. So yeah, the problems come in, but if you be stupid enough, ask a lot of stupid questions, find out a lot of things you don't know, you will find the answers.
Now, one thing you've said is that finding joy in your work is so important. Can you shed some light on your philosophy?
I enjoyed my 50 years. I have worked like almost like 51 years now, probably. And I enjoyed a couple of things. One is the team I worked with. I could trust the team. I had fantastic relationship with me, with my team, with my bosses, with my subordinates. It was a lot of fun because when you have trustworthy team, you don't have to worry about being stupid sometime, being like artificial intelligence. If you want to, not that artificial intelligence, but intelligence, you think you are intelligent, but if you have a trustworthy team, you can share. You can share your ignorance. You can share your thought process and let people criticize it. So you can come up with you. I used to come from conferences. So I have 10 ideas. We sit down on the table and we find out nine are stupid ideas. So, but there's one idea which comes in, then you work on that idea and you work on that and you find out ideas which are good. So my 50 years, I worked on five, six different technologies, have been a lot of fun because the people I worked with at NRL, a team of 25 people, even today, it has been like more than 35 years I left it. Even today I go, that team trusts me and I trust the team. Why? Not only trust, we share everything. When I was working in the industry, he's now chairman of Comscope here in Hickory. He hired me and he told me that Ish, in my company, he bought a company from a telecom company, long story, but he bought a company and then he said, in my company, even the janitor have one stock. So everybody shares in it. And the sharing becomes very, very nice because then everybody is motivated and doing the things, bring a success to the group or it's like a team, success to the organization. So sharing is very important because uh, sharing also it creates the fear of the other people. 80% or many times I find in research lab, people are fighting whose name will go on the publication, whose name will not go on publication. Sometimes author puts only two names. If in my group, if people have worked on a program, have contributed to the problem, everybody's name goes on the authorship. Then not only that, I have, like you mentioned, more than 100 patents. And those patents are not mine. They are my team also. The people, 25 people I had in the group, they contributed to that. I just did the mouth service. But a lot of the work was done by my team. So I was able to work on licensing these patents. We licensed like 50, 60 patents to the private industry. We got royalties. It is unthinkable that is other way is against the second law of thermodynamics, as I call it. The I was in the government and we are selling to the private industry, and private industry is giving us the money. Normally, the government gives the money to the private industry, not the other way around. We were able to get the royalties from them, and those royalties were distributed among all the team members. They were very happy. So obviously, we had a fantastic team. We still have that team, and so that does work. That motivates people. So so to trust and share is very important. Also, your work life becomes important. If I don't trust my team, normally I used to fly a lot to market my program. Market, you have a new idea, but new idea has to be marketed to the people who have the money, who have the funding. And so to market, I had to go out. So if I had to worry about somebody not doing the work back while I'm gone, then it becomes very difficult. I can't enjoy my travel. I can't enjoy the inside. So if you are a trustworthy team, it does work. And also one thing to the researchers, I want to tell you that the power of money, this is not, you may not have heard of, is inversely proportional to the technical knowledge. Let me give you an example. If you're a Nobel Prize kind of scientist, he will work only with like a half a million or $1 million funding. He will have him and maybe two or three technicians. Then you get high level professors or high level researchers. They will have maybe 10 technicians. They will have $10 million power, right? Then you have a stupid professor like me. I'll have maybe $20 million program because I'll sell my program to a lot of other people and things like that. But then you go to the master's level or bachelor's level people who are the program managers in the government or other places working on the big program. Their power of money is like 50 million, $100 million. Then you get to the politician, their power of money is billions and trillions of dollars. So power of money is inversely proportional to the technical knowledge. That's why if you want to get the money, if you want to get the funding, you have to speak in a very simple language. You cannot speak in a scientific language because the person who has the money doesn't know science. He has the money, but he will not have the science. So more easier you speak, more money you bring in.
Well, and I think you talked about the importance of your team and your team members, and
Yes.
that in the different environments in industry and in government and in universities, the team's members have different strengths.
Yes.
And you, as a team leader, need to optimize them and take advantage of each of their skills.
It is true. Working in industry and in government and university is very different. Let me tell you why. In industry, you have focused team. You have 10 people working in the team. They have the same motivation. If they don't work on that motivation, they are gone. So there's another way. They are fear phenomena too. In order to maintain, you have to work, and people do work hard. When you go to the government, I found out then in government I cannot use the same idea for motivating people as I did. Here you have in the government people who have permanent jobs. They have permanent jobs. You can't just let them go or something like that. So you have to motivate them with a different technique because it's like you have married somebody, you just can't say, okay, one fight and you're gone. So you have to motivate people with different technique. And I learned that technique. In industry, I had to use one technique to motivate my staff or my people. But in the government, I had to use different thing. I had to make them partner in the crime. They make partner in what we are doing so that it becomes their project, not my project. When it becomes their project, they are motivated.
So now you've worked across industry and government and academia. What would you change in academia if you could change one thing?
Well, academia, when I came here 14 years ago, I was wanted to set a big program, I hired some people and everything. But academia is very different. One of the things I found out as soon as I hired a professor, as soon as I hired him, then I got him, well, not I got him, he got a tenure track position. If you get tenure track position, in order to get a tenure, you have to prove that you are an individual worker. Means you can work in the team.
Right.
So this so-called tenure system is an anti-teaming effort. So I learned that. So in university, not two professors don't work together, which is kind of crazy because in today's environment, somebody is good in bringing money, somebody good in getting the idea, and somebody is good in implementing it. You need all three of factors. So teaming is extremely important. That's what I plead. I'm trying to tell the professor, trust and make a team, and don't go on a short-term benefit. Don't go on a long-term benefit because we have a team. When I did my graduate work or when I did my PhD, I had three professors, Montrose, Macedo, and Litovitz. One was the idea guy. One was able to get anything done with the university, and one was could take care of the problems. He could write the proposal. He could do so many other things which are really needed. All three of them came up with a fiber optic technology, which I worked on. Luckily, I mean, I benefited from them a great deal. They were very good in, yeah, they developed the fiber optic, a different process of fiber optic. They licensed it, made a lot of money. Then same technology they use for nuclear waste disposal. If you remember, there were a lot of money was wasted and still being spent in nuclear waste treatment because we have so much nuclear waste around the country. And they used that technology, set up a company, and all three of them made a lot of money. They became multimillionaires. So teaming, a professor's team, and that's my plea, it work doesn't go waste. Work always shows off. And that's why I tell people I have if they are students or they are things, five things you have to remember. Hard work is very important. You have to do the hard work. Anybody can do the hard work. I mean, in any job, you have to do that. Dedication is where you have to be dedicated to the work, and your boss is everybody recognizes if you are dedicated, you're not. Third, loyalty. Extremely important. Wherever you are working, you should be loyal to that place. I know in today's environment, we change jobs back and forth and here and there. So loyalty is not a big factor anymore. There used to be time when companies used to hire and you were hired for lifetime. That's not there anymore. I understand. But as long as you're working, you should be loyal. And then people can determine that then you don't worry about the boss or anybody because you're working hard. Everybody likes you because if you work hard, you produce, then people will like you. Bosses will like you, and every boss like me. And fourth is trusting. You need to have a trusting team. Is very important. And finally, you share. If you get the benefits, you get the limelight. You share the limelight among your team. Sharing is very important. So these are the five things at least I have used, and I have my. I didn't have to ask for even raise or something. I used to get nine raises in 9 months or something. Automatically, I used to get that. So when you work hard, you produce, you work loyally, it pays off.
Well, and I think what you've emphasized is the importance in teaming, emphasizing different people's strengths and weaknesses, and also giving them credit, be it through authorship or including them in the teams
Sure.
or including them in money and these kind of things. So what you have talked about is that invention doesn't really stop at discovery, and it requires partnership, protection, and persistence. How important was patenting in turning infrared fiber from a laboratory curiosity into a globally adopted technology? And how should today's inventors think about IP as a part of the creative process?
I think it's very, very important. I can give you an example. I was working in the silica fiber technology. I don't know how much time I have, but there was a one in the when you make the fiber, fiber is, believe it or not, is stronger than steel wire. A glass fiber of equal diameter is stronger than steel wire. But you cannot maintain the strength of the fiber because if you touch it, you abrade it. It's a brittle material. As soon as it's abraded, as soon as a little tiny defect is put in, it will break or it becomes weak. So key part with the fiber technology, well as people discovered, is that if you draw a fiber, while it is pristine, while it is still being drawn from the hot furnace or from the rod you are drawing the fiber, you need to coat it with a polymer coating, with a liquid polymer coating, and then you have to cure it to make it solid so that you can draw it. So when you do that, the fiber strength is maintained. Then you don't touch the surface of the fiber. So, but the problem was you put a liquid coating uh, on the fiber with a cup or with a cup, and then you're drawing it down. Then how do you cure it on all sides? And they used to put four lamps on each side so that all the sides get cured. So when I started my career or with a company, I was trying to build a draw tower like that. So I called the UV lamp people, and we were talking about it that you had to design my lamps like that. Then I came up with the idea that I had ellipse. In a ellipse, there are two focal points. So whatever goes through one focal point goes through the other focal point. I thought of that. So I asked him that, can you make me an elliptical cavity? He said, what do you mean? I said, I want an elliptical cavity, and then I want to put my UV lamp on one focal point, and I want to put my fiber on the other focal point. So that whatever the rays come out of this UV lamp go all around, they strike the reflector, they go through the fiber, everything strikes the reflector, goes through the fiber. So fiber gets cured on all sides. And it was great. The guy started doing that and I got the lamp. But I was working with smaller company. I didn't patented it. It was not patented. And then in my career, I visited 100 labs at least throughout I have traveled to 50 different countries, and I have been to hundreds of laboratories of different people. I'm one of a unique guy from that. And everywhere where I see that elliptical lamp, and somebody else patented after me, and they got the credit for that, and the guy who invented didn't get the credit for it. So I was really upset about it always. Then when I went to NRL, I made sure whatever the ideas we get, we are going to patent it. And with patent protects your ideas. Also, it gives a motivation to the people because it's like feather in your cap. Uh, when we get a patent about it, we feel very good. We don't know at that stage whether it will be useful or not. But if you have 100 patent, I'm sure at least 10 or 20 of them will become very useful. So protecting your technology, protecting your thing, one, it gives motivation. Second, it protects you. I mean, if you have worked hard on it, you should be benefited. You should be rewarded. And what is the reward? If you have patents, you may get royalties, you may get other recognitions. So that point of view is very good. Publication is very important too, because then people recognize you are a big researcher. But publication, patenting, both are very, very important.
Excellent. Excellent. Well, at this point, why don't we see if there's any questions in the chat? It's not up on my screen, so I'm going to ask our moderator to read it.
Ariana, you can take the share out, screen share.
I'll read the question for you. What can we do to get more out of K through 12 students as excited about inventing as you are?
Well, I think you have to show them as, first of all, give them the lab tours, give them the tours in the labs, show them how inventions occur, or show them small demonstrations that what are the things can be done. AI is, for example, on the computer, you show that, hey, computer, you do this thing. A lot of these things happen so that they become curious about it and they start working hard on it. Also, there are so many of these what you call fairs in which the little students, I know my kids used to go to them when they were young. They were used to demo, they used to get projects from the teacher and grow plant and how do you grow plant bigger, better or something. So you always give the demonstration, talk about science, talk about the rewards of scientists. Unfortunately, the problem I'm getting now at the university, recruiting people in, I have PhDs, students openings, but finding US students for PhD program in science and technology is very difficult. Well, of course, they are there, but I'd like to see more of them, more choices. So exciting people from K1 to K12 in science and technology is very important. And I plead all the teachers and everybody that they should work hard on making science as very attractive. Science has make them, half of the problem is kids also become, oh, I don't know math, it's difficult. Half is psychological. People just assume that it's difficult. And a lot of people are capable, but this assumption of being difficult comes in the way. So my plea is that teachers make it easier, make it simple for them, make them excited in science.
So we have a question in the chat from one of our professors here at UNC Charlotte, Dr. Helmy, and he says, how do we excite faculty about innovation? Where can they get more credit for promotion through publications and conferences and patents?
Okay, the promotions in faculty these days, one of the key thing is you have to bring in the money. I mean, any professors, uh, you have to write new proposals, new ideas, and then bring in the money and create a group so that you are exploring a lot of things. You are having a research program. When your research program, automatically you are going to get promoted. If you bring in the money, if you bring in funding, the people who get more funding, they always get promoted. And and that, how you can do that? Make a team. Get another professor working with you and make a team with him that, hey, you are going to do this and I'm going to do this. And if you make a team, you can bring in more money, you can get recognized more, and that's the way to go. but you don't go. I mean, problem is professors don't go there.
So your advice is to build a team
Build
that
a
has these
team.
different skills, and then you all can go out and
And
promote more money.
if you bring in money, if you show the success in the program, as I said, promotions automatically come. I was rewarded always. Whether I seeked or not, but I believe that if you do the hard work, if you do the successful work, if you show the progress, if you do the things, rewards do come to you.
Well, let me ask you a follow-on question for young inventors and for old inventors too. What advice would you give about trusting an idea when the math says 2 + 2 = 4, but your instincts and your curiosity says 2 + 2 might equal 5?
Yes. Well, yes, actually, that's true. When you combine two different technologies, you combine two different ideas, you get a bigger benefit than the individual ideas had. So, as I showed to you before, that we applied the purification technology to the chalcogen I5 with them low loss, and that became a huge thing. Now we are applying the moth eye idea to a laser optics, and it's becoming a huge idea. It's solving a lot of problems. So you always combine one idea with the other idea, you get third idea. And third idea a lot more benefit than the other one. Those who are in physics, they already know nonlinear physics. When you're pumping something with a very high intensity, you get different phenomena going on. And those different phenomena have produced lasers, have produced amplifiers, have done a lot of things. So there's always a benefit of when you are combining one idea with the other idea and get a third idea.
That's brilliant. That's
Well,
brilliant. Dr. Aggarwal, thank you so much for sharing your time.
oh, you're
I
welcome.
mean, today's conversation reminds us that transformative innovation rarely follows a predictable path, and it requires patience, persistence, environments where ideas can be recognized and supported long before their full impact is clear. And I think it also requires leadership to recognize how you can put these wonderful teams together to be able to allow 2 + 2 = 5. And your career shows what becomes a possibility when deep science is paired with long-term commitment, and when patenting serves not only as protection, but as also as recognition of inventive achievement and the foundation for continued innovation. And that recognition enables ideas to move forward, attract partners, and ultimately reach the world. The idea that 2 + 2 can equal 5 captures the essence of invention, trusting curiosity, embracing uncertainty, and believing that the outcome can exceed the expectation. So, Dr. Aggarwal, thank you again for your leadership, for your contributions, and for reminding us of the joy at the heart of innovation. Thank you, sir.
Thank you, Laura. I just want to tell you that at the end, I really enjoyed my 50 years. I'm almost 80-year-old. I'm still working and I'm really enjoying it. It's not that somebody is dragging me from someplace or I need the money or something, but I just enjoy it. And all the colleagues I have at the university, in the industry, in the government have been great to me. I cannot complain about anyone. I can knock on anybody's door and I'll be welcome. So I had a lot of fun everywhere I worked. And my family, I should thank them. I forget about the family, my wife, my children, and all the relatives, they have been great to me. I don't have any, God has given me everything, I guess. And I'm very, very happy for that.
Thank you. Thank you, Jamie. We'll turn it over to you.